Welcome to Wireless Future. I'm Emil Björnsson. I'm a professor at KTH Royal Institute of Technology and an associate professor at Linköping University. And this is going to be a conversation just as last time with Erik Larsson, who is a professor at Linköping University. How are you?
Oh, quite good, Emil. How are you this morning?
I'm fine. I hope that this video studio is going to work very nicely this time, even if it's early in the morning. So last time we were talking about massive MIMO, this new 5G technology where you are sort of directing signals towards users in different way. You can serve multiple users at the same time and so on. And this is something that we have been working on for a while. But when I started at Linköping University 6 years ago, I remember the first thing you told me was that shouldn't we write a paper about the myths that is in this topic? Can you tell me about your ideas there?
Oh yeah, so the myths paper, wow. I think this all originated in, obviously discussions that you and me had, and also that Tom and had with us. And also the fact that I had been at the time traveling around and giving talks and talking to a lot of folks about massive MIMO all over the place. And I have heard so many nonsense claims and so many misconceptions that I thought we're going to do something about this. We're going to put together a talk and a paper on the topic. And I think the trigger for me was really a conversation I had with a highly respected fellow at a conference. This must have been back in, 2013, 2014 perhaps. And we came to talk about massive MIMO. And he told me, so, well, Erik, are you still pushing massive MIMO? And I was like, yeah, I think it's I can't really think of any other topic that I'd like to invest in. And he was like, yeah, but massive MIMO is not going to work. And I said, okay, so why is it not going to work? And he told me, well, massive MIMO is not going to work because of noise. And I said, so what do you mean because of noise? Well, with 100 times more antennas, you'll have 100 times more noise. And that's when I really decided that we're going to do something about this. I went back and we spoke, Emil, and we decided to write the myth paper.
Yeah, so I think the interesting thing was when I started I think it was 2014 in the autumn, then Thomas Marcetta was also visiting us at that time. So we had like 2 sessions, an hour each, where we were sitting down around the table and just brainstorming what were the misconceptions that we have heard. So I think all these 10 myths that are in the paper are things that one of us or multiple of us have actually heard in reality. So it's not something that we made up, no. Right?
Yeah, no, that's entirely true.
And I think for the 6 years that have passed now, a lot of things have happened, and now massive MIMO doesn't sound as controversial anymore. It's actually being deployed. I was in a conversation last week, and I heard that Huawei have been selling 1 million massive MIMO base stations, half of them deployed in China, for example. So I was thinking that in this edition of our podcast, we are going to talk about the myths. I have selected a few of them, and I will read up the myth and give a little bit of background, and then we will talk about whether we agree with our statement from before, what was the contrary argument towards the myth, and have anything changed since the last time. Are you ready to go?
Yeah, sure, go ahead.
Yes, so one myth was that massive MIMO is only suitable for millimeter wave bands. And I think sort of the argument there was that if you are building an array of antennas, you need to put the antennas half a wavelength apart. So therefore the arrays are going to be large and they're going to be too large to deploy them in reality. So what is the counter argument here?
Well, I think the obvious counter-argument is that there are already products out there, right, with 64 or 128 antennas, and these are all for lower frequency bands. So reality caught up pretty quickly here. That said, it's also clear that at millimeter wave bands, you will need some form of antenna arrays just to maintain the link budget. But I think it's still fair to say, that the main utility of massive MIMO is going to be at the lower frequency bands.
Yeah, and I think last time we were talking about this MIMO arrays that are in the 2.5 and 3.5 bands, for example. But if you talk about really low bands, say below 1 gigahertz, don't you think massive MIMO is going to be very hard to deploy in such setups?
Yeah, so why would it be hard to deploy? I think this is one of the remaining myths. You could think of in terms of array design, you could think of like conventional panels, right? There would be like some sort of rectangular kind of blocks that you put up on towers. But there's no reason for why a MIMO or massive MIMO array would have to look like that. I think it's rather that the arrays we'll see in the future will be composed of small sub-arrays or even antennas that will be like naturally integrated into objects, into buildings, into who knows what structures. I mean, and so I think that will likely be the main next shift of thinking that we'll see in the community, that, well, massive MIMO arrays don't have to look like panels as we think of them conventionally.
So what if we could squeeze the antennas closer together than half a wavelength? Would that make any sense? Could we use that trick to make the array smaller?
I think that that's something we'd like to avoid. I mean, you know, squeezing antennas closer than half a wavelength together creates all sorts of electromagnetic trouble, right? With mutual coupling, with high internal currents and so forth. I don't think that's the way to go. In addition, it also makes the fading correlated, so which might be a good or a bad thing depending on how much you know about this correlation and so forth. So I would rather think to the contrary, that we'd like to spread the antennas out. We'd like to make the arrays physically larger, but the arrays won't necessarily have to look like antenna arrays conventionally have looked like.
But if we are restricting ourselves to the type of deployments that we have today, like we put up a array on the rooftop, or particularly on the mast, where you have like a requirement from the weight and the wind load that is limiting us, don't you think that the arrays that we have now are as large as they get?
That's a good question. I mean, so about these masts, well, I think that, you know, I mean, ever heard of reinforced concrete? So this is just a matter of how rigid you build the masts, right? And I think there might be a challenge here for civil engineers. So hey, all civil engineers out here, I mean, I know what you can do. I've been up the Taipei 101 skyscraper, 450 meters tall, and talking about wind load, I mean, so there is this sphere at the top floor. If I remember well, it was like a 5-meter diameter and it weighs like 600 tons. So, and then the maximum deflection when the typhoons hit were like a meter or something. So if we can build that, I'm sure we can also build towers that could support, you know, an antenna array with a couple of hundred antennas. Obviously, there is a cost-benefit trade-off here that has to be worked out, right? And it's very possible that the masts that we have been using so far and the particular structural design that we see in them and that we see in the gadgets that we put up on the rooftop today aren't sufficient to carry the load that would be incurred if we had like an array with 500 antennas. I'm not quite sure, but I just don't see that this would be a fundamental problem. I think it's a matter of just designing the arrays properly. That's what I think.
Okay, so it seems like this myth is indeed a myth then. So let's move on to the next one. We had the myth saying that the case for massive MIMO relies on asymptotic result. And I think here the sort of idea was that the first paper on massive MIMO was about what happens if you have an infinite amount of antennas, which I guess you could deploy if you have an infinitely large universe. But anyway, there have also been a lot of focus on phenomena that appears when you have a very, very large array, sort of channel hardening, where the fluctuations in channel quality reduces, and favorable propagation, which is saying that you can tell users well apart, for example. And isn't massive MIMO really about this huge number of antennas? And is this a myth, or is it? Yeah. Is this a thing?
Yeah, see, Emil, I think this is such an unfortunate misconception with the asymptotics. I mean, you know, I think the number one question to understand here is how many antennas in a massive MIMO array that are really useful to have, right? And this is all determined by the channel coherence, because the channel coherence tells us how many orthogonal pilots there are room for, and consequently, how many terminals can we learn the channel to, right? So for lower frequency bands and high mobility, this number is like in the order of 30 or maybe 40 or 50, but in that ballpark. So with multiplexing to 30 or 40 terminals, then you need at least the 30 or 40 antennas. And if you go above, say, 3 times that, so above 100 antennas, then the utility of adding extra antennas is at best logarithmic, because you can't increase the multiplexing gain, you can only increase the array gain, and that gives you a logarithmic gain in spectral efficiency. So the numbers of antennas that you would want to deploy in, say, an outdoor macro cell environment would probably be like 100, possibly 200, but certainly not like 10,000 or some number like that, right? And I think it's highly unfortunate that academia has helped propagate this misconception that massive MIMO in any way relies on asymptotics. I mean, obviously we can find countless of papers that talk about, mathematical models and then let the number of antennas go to infinity and make various claims what happens in that regime. I'm not saying that there aren't cases where such analysis could be interesting or useful, but I am saying forcefully that I think that we have contributed, probably you and me have also contributed to this, but academia in general have contributed to creating the notion that massive MIMO analysis or massive MIMO technology in general would rely on any sort of asymptotics in the number of antennas, which is simply not true. And to this day, I can still find this statement being made, right? I still hear this being said, I still see this being written in papers. So I think we have still an educational mission here to fulfill, to debunk all this nonsense.
Yeah, and I think this happened still when it comes to us submitting papers for review, that reviewers might say that, this isn't really about massive MIMO because there is no asymptotic analysis in the paper, for example. But since there were all these focus on the asymptotics, I would say that it led to us overstating the importance of this phenomenon of pilot contamination that turned out to be a major factor when you had a lot of antennas. Do you agree that we were sort of overstating the importance of caring about that phenomenon?
I'm not sure, Emil. I mean, I think, it depends on how strong prior assumptions you make and how much prior information you have access to, right? I mean, I'm well aware of your papers on unlimited capacity, which basically state, as far as I understand, that if you have strong enough priors on your channels, your channel correlation matrices with good enough accuracy, and then you let the number of antennas go to infinity, then under relatively mild conditions on the channel correlation matrices, then the spectral efficiency goes to infinity. That said, I still hold the view that for modest number of antennas and with, say, realistic or reasonably low prior knowledge on the fading correlation, pilot contamination is a phenomenon that we need to deal with, and it can be dealt with. I mean, the simplest way of dealing with it is just to reuse the pilots more sparsely geographically, so that you use a reuse pattern for the pilots, which is like conventional frequency reuse, maybe a factor 3 or 4 or 7 or something, and then you push the problem. You don't push it away entirely, but you push it down to a level where it's no longer the dominant source of impairment. So in that respect, I fully agree. I mean.
Yeah, I think that is also the main point, that if you do a good design of the system, it won't be the problem anymore, because it is something that might be a limiting factor in the asymptotic regimes. But if you have small enough antennas, as you were describing, and you do a good system design, irrespective of if you had a prior that I was assuming in my paper or not, it's not going to be the main limiting factor.
Yeah, and that's an important point, I think, to understand. I mean, we can push this problem away for all practical purposes through appropriate pilot reuse.
Yes, so let's move on then to the next myth. This one was stated like this: a new terminal cannot join the system since there is no initial array gain. And I think the sort of idea here is that when you have many antennas, you are sort of forced to have a very directive transmission. And if you if you at any time used a binocular and tried to look at something far away, you know how hard it can be to sort of look around and try to pinpoint the place where you like to point it at. So the more directive it is, the harder it is to find the place that you would like to focus something on. And what is the counter argument against something like this?
So the question is really, I mean, whether, now if you have a massive array of antennas and you want to transmit in no particular direction, so you want to broadcast some paging signal omnidirectionally or some system information omnidirectionally, then that would be difficult. Is that the question? I mean, so yeah, then I think the obvious counter argument is that, just apply any diversity transmission scheme of choice, right? Space-time coding or space-time block coding or anything you like. And the net effect of that is that transmission is going to be omnidirectional. So it's very hard to see why this would be an issue in practice. I mean, well, you could think of like pilot overhead in the downlink being an issue. If you have like 100 antennas and then a space-time block code for 100 antennas, you would need like 100 orthogonal downlink pilots, and that could eat up resources.
Yeah, that was what I had in mind, sort of.
Yeah, so no, but that's a legitimate argument, I think. But I think the point here is that you wouldn't necessarily need to use all these 100 spatial degrees of freedom. You could like group antennas together and have them transmit sort of like the same signal, and the effect would be something that's almost omnidirectionally. Here's the thing: if we are in independent Rayleigh fading, then in fact it doesn't matter which beamformer. If you just beamform with an antenna array, then in independent Rayleigh fading, that's going to look like omnidirectional transmission. So now, if we are in something that's reasonably close to independent Rayleigh fading, then it'll be enough to just beamforming in a few random directions using a diversity transmission scheme, and that will appear as an omnidirectionally broadcasted signal. So it is, strictly speaking, I mean, it's a valid argument that with a 100-dimensional space-time block code, you would need 100 pilots on the downlink. But in reality, we could use space-time codes a much lower dimension and achieve almost the same thing. So I'm really hard to see that this lack of array gain for new terminals joining the system would be a true issue in practice. And on top of that, I think it's also the case that the number of bits by large in a wireless network that are used for the purposes of paging and transmission of system information, those bits are very few in comparison. So even if we don't use like the most efficient means to transmit them, it doesn't matter much in the end. I think that's really the bottom line here.
So if we are able to squeeze out much more data transmission when we have added the user into the system, we could sort of, if required, spend a little bit more on actually letting the users access the network.
Yeah, I mean, I think that's the right way to think about it, that we amortize the, say, effort for the initial access over all the payload that will subsequently transmit, right? And then in comparison, the efforts and resources that we spend on the initial access will be vanishingly small.
Yeah, and I think that also even if we can't squeeze out the full sort of array gain in the transmission of this type of information through space-time block codes, you can still be in a situation where you are better than the conventional system, but not as good as you will be in the data transmission, and that could be fine as long as you can add a user into the system. Right.
Yes, I entirely agree. I think that's really the point here.
Okay, let's move on to the next myth then. Massive MIMO requires high precision hardware, and I think this is sort of the question here. If you're building these arrays, you will have to sort of take all of the hardware that we have in a radio of today and put them behind the antenna, and the radio is larger than the antennas. We get a very bulky type of system here. And then the counter argument was that we are having a system where we are sort of less sensitive to hardware distortion, or what was the counter argument here?
Yeah, so I think the counter argument that we made in the myth paper was that the hardware, this air quotes hardware distortion that originates from all sorts of effects. I mean, nonlinearities in the hardware might be the most important one. That these hardware distortions average out when you have more and more antennas. And I think that is true at least partly, but I also would like to add, and this might be the single myth here that I would express a few reservations against, in retrospect, because there are really two kinds of effects here, right? One effect is in-band. That the signal within the band will be subject to distortion. So what happens typically when you have a nonlinearity is that the signal constellation starts to smooth out a little bit and doesn't appear as sharp at the receiver, and that will increase the bit error probability and so forth. And so that's the first effect. The second effect is that certain types of hardware impairments also create out-of-band radiation. Yeah, and this out-of-band can be really a deal breaker. Typically you want the out of band. If you have a band allocated for your transmission, then you want to make sure that whatever is spuriously emitted outside of that band is like 40 or 50 dB below what you are in band. And now if you have a nonlinearity, then what this nonlinearity does is that it causes transmissions from your signal band to leak outside of the band. And the problem is that this out of band distortion doesn't average out over the antennas in the same way. In some unfortunate situations, this out-of-band distortion ends up being beam-formed into specific directions. And then if somebody is standing in those directions and listening in the adjacent band, using the adjacent band for some communication link, then that link could suffer a lot. So I think we've got to be careful here. It is certainly true that in many cases of interest, the hardware distortion errors just average out. So in that respect, we could get away with lower quality or cheaper or less accurate hardware as compared to conventional wireless links. But we also had to be very aware of this out-of-band issue, and particularly the phenomenon that out-of-band radiation in certain situations ends up being beam-formed and could cause a lot of harm and trouble. Yeah.
Yeah, so I think one of the issues has been that people in academia perhaps have been focusing way too much on the in-band performance there. And you typically have the feeling that you start with the conventional discrete time system models, which is only focusing what happens within your communication band, and then you're not thinking about what happens out of that band. And then there's also, in addition to the nonlinearities that you described, there is the analog to digital converter that you have in the uplink. And there's a lot of work that have been showing, you can get away with 3-4 bits instead of 15 bits as we have conventionally. And the argumentation is that 3 to 4 bits per each antenna, if you have 100 of them, that's 400 bits, and that's much more than 15 as you would have with a single antenna. But that is certainly true when it comes to the in-band performance. But if the whole point of having 15 bits instead of 3-4 in a conventional system was that you should be able to deal with this type of out-of-band distortion that you mentioned, another base station is transmitting or another user is transmitting in a neighboring band, well then it doesn't help that you can do things in the simpler way inside your own band if it's the actual limitations come from the other adjacent bands.
Yeah, I think that's a good point. All these papers on 1-bit ADC in the uplink, or even 3 or 4 bits, they are academically, mathematically beautiful, but they are really only practically relevant for a world with, where the receivers have ideal filters, which we know don't exist, or where there aren't any transmitters in the adjacent bands, which we know, the spectrum is all crowded, right? And there will be transmitters all over the place. So I think we got to be careful here. I think, now speaking of the uplink, the effect of a blocker, so a strong transmitter in an adjacent band that comes in perhaps with line of sight, well, unless you have extremely sharp filters, your receiver front end, before the AD converter, then you aren't going to get away with a single bit or even 3 or 4 bits. You need a quite high dynamic range there to deal with the out-of-band interference.
Yeah, and I think when I was sort of drafting text for this, when we were answering to this myth, one thing that I had in the back of my head was that, well, are we building new base station based on the past type of hardware, which is designed to be able to transmit the signal from one antenna with strong power and requiring a lot of advanced hardware in order to deal with that? Why don't we build an array based on sort of the chipset from mobile phones or something like that, starting from that and then build up, like having 100 chips from mobile phones and building an array based on that? And I think from that perspective, it might be right that you could use that type of much simpler hardware and still be able to, from a big array, get a good transmission. But since you then are adding up the power from many transmitters, you still have these out-of-band requirements that might be harder to fulfill with that base station, because you have sort of different requirements on the handset and on the base station.
Yeah, I think that's really the case here. I mean,
so let's take one more myth here. So it says, or actually I merged two of the myths because they are sort of on the similar type of topic. It says that with so many antennas, the signal processing and resource allocation complexity will be overwhelming. And I think we had one myth that was about the baseband processing. Okay, you have a lot of antennas, you need to process them together in order to sort of distinguish between users in the uplink, for example. And the complexity of that would grow either linearly or polynomial with number of antennas, so we have a higher complexity there. But then you also have maybe even more problems when it comes to the resource allocation things. Like you need to solve a problem to figure out how you should divide the power between the users, or you need to sort of deal with scheduling, which user should be served when, and scheduling type of problem, or it's a combinatorial problem, which usually have a complexity that grows exponentially with the number of users, for example, that you have to choose from. And if the whole idea is that you have a lot of users, not just one, then this will be very complex. So what was the counter argument against these type of things?
Well, so I think first, I mean, about the resource allocation, right? So one of the features of massive MIMO transmission is channel hardening, which effectively means that the effective scalar signal or channel seen by each one of the terminals will be nearly deterministic, which means in particular that it doesn't depend on frequency, right? So for example, I mean, in an OFDM context, then every subcarrier is equally good. And this takes away the need for scheduling in the frequency domain. So in that respect, I think it's to the contrary. I mean, scheduling a resource allocation becomes easier in massive MIMO as compared to in conventional transmission.
But don't we have the issue that if we conventionally have a system where you only schedule one user at a time, and now of course you can put it on any frequency, it doesn't matter. But if we are scheduling users that are at the same time and frequency, but now you need to be able to separate them spatially, don't you have the problem we need to compare all users and figure out which ones can you separate well in the spatial domain and which can't?
I think in a way you might have this issue. I mean, if you are like in line of sight and the users are very close in angle, then spatially multiplexing them might not work, and you would have to give them like orthogonal frequency resources. But with that exception, which by the way doesn't seem to occur very often, then as soon as we have like a fading channel with enough randomness in it, then all the subcarriers will be statistically identical, and it doesn't matter whom you give which portion of the frequency domain. And ideally, I mean, what you want to do is to give everyone the full bandwidth, right? So multiplex spatially rather than over the frequency domain. Is that what you meant, Emil, or did you have something else in mind here? Yeah.
No, that was sort of the issue that I think that to some extent we might have overstressed that you can just put in users wherever you like. You never need to care about scheduling anymore.
Yeah.
I think there are situations where you need to care about it, particularly if we don't have many hundreds antennas, or we have uniform linear arrays that are several meters long, but you have a panel that is of the square size. Well, then maybe you can't separate users well in all type of situations.
Right.
But it seems to be not as much of a problem.
Yeah, I think that might be true. I mean, you're right. A lot of these, say, foundational results in the massive MIMO literature were built on fading models with independent fading at the different antennas, or uncorrelated Rayleigh fading, I think is like the baseline model, right? And whenever, I mean, in reality, we won't see that in general. And with more extreme models like line of sight, it could very well happen that users are close in angle, and then that's true. I mean, spatial multiplexing won't work, right? I mean, if they are if they stand still and are close in angle, we have to multiplex them in the frequency domain. So there are cases like that will have to be dealt with here. That is true.
So what about the baseband complexity for everything you need to do, that pre-coding and channel estimation and things like that?
Yeah, so, you know, when I started to work on massive MIMO myself about 10 years back in time, then my own perception, and I think the commonly held view in the community, was that baseband signal processing for massive MIMO is just going to be plain impossible. I don't think anyone had even seriously thought about it until like you and me did a calculation many years back now. I think it is in the MES paper. You know, just back of the envelope estimating. So how many flops would actually be required to do all this, right? I mean, there's maximum ratio combining and zero forcing matrix inversion and all that. And we concluded that this is not a big deal. It's not like you need a supercomputer to do it. You probably could do it on a, maybe not on a standard DSP, I mean, but certainly on a circuit that you could integrate easily into a base station. And then a few years back, our colleagues at Lund showcased a chip that they had built that did real time on a 20 megahertz bandwidth with, if I remember well, 128 antennas, and zero forcing multiplexing to, I think it was 8 terminals at the time, right? And it was in real time with all the matrix inversions, all the matrix multiplications and all that. And the power consumption of that chip was like 50 milliwatt. And I was like, this is not only amazing, it's like, seems close to impossible, right? And now, you know, to be clear, I think there are parts of the processing that weren't included there, like FFTs and other things that do scale, I mean, with a number of antennas. But even accounting for that, I mean, you know, doing this on a single chip or on a circuit board is just no big deal whatsoever. At least not when we stay in that regime of, say, 100 antennas, maybe 10 users multiplexed at the same time, which is, I think, where massive MIMO state-of-the-art implementation stands today.
Yeah, so I think in the first papers there were sort of always said that, oh, the complexity is going to be so hard to do, so therefore we need to do matched filtering, or which is also known as maximum ratio combining and transmission. And I was always against that because it felt like a waste of antennas if you are going to build this advanced system and then you are going to use the simplest possible type of processing. So I was very happy when I eventually saw that, okay, the complexity isn't that hard. In particular, you just need to build a dedicated circuit or do a good implementation, and then it works. I think what I then heard from our colleagues that have been implementing this type of thing in designing circuits is that the real issue is not actually the complexity, but what they call the interconnect. How you're taking the signal from all these different antennas and gather them at one location where you can do the processing.
Yeah, I think that might very well be true. I mean, and this goes back a bit to what we talked before about the array design. And so my view here is that we probably shouldn't be really thinking in terms of centralized, like panel-style antenna arrays with cables. I mean, a cable from each one of the small antennas that goes down to some sort of baseband processing unit, or, you know. I think we rather should be thinking of like small sub-arrays that contain only required electronics and at least parts of the baseband processing, so that as much of the processing is done locally close to the antennas or in these sub-arrays. And that way we would, I think, avoid this interconnect problem. So I believe that this is likely to be like the next step in the development of processing technology for massive MIMO, to build small independent sub-arrays where you can actually handle all the baseband data, and where interconnect is not a big deal, and then bring this all together to digitally then to a central point somewhere.
Yeah, I think that the vendors or also the operators have the hope that they could put a lot of the processing in a so-called edge cloud computer, because you would like to be able to change the algorithms without having to climb up in the mast and change things there. So I think what is sort of done today in the 64 antenna arrays is that you have some kind of compression algorithms within there. You take your 64 dimensions, you are trying to figure out in which dimensions is there strong signals, then you compress them in the digital domain, send the rest to this edge cloud, and then you do the processing there. So there might be some trade-off about how you are building the system in order to deal with these interconnect problems.
Right.
So now we've gone through maybe 5 or 6 of the myths that we have in the paper. We had some other things on the table, and I think in particular there were one thing that we were first discussing as the 11th myth. I think you were putting forward that massive MIMO can work in FTD operation as a myth, and I was saying that, well, first of all, we will never get the paper published if we are making such a bold statement, but also it might not be entirely true. It's hard to quantify what does it mean that it works or not. And then the day after, you came back to me and had this new idea that we're going to pose it as a critical question instead of a myth. Can it work in FTD mode? And now people really need to figure out if it can work or not. Do you think we have received a question now, 6 years later, about if massive MIMO can work in FTD mode?
Yeah, see, I think the point here is that what does work mean, right? Of course it works, but it's never going to work as well as it does in TDD. And I do think that there is a growing consensus in the community that TDD reciprocity-based beamforming is just superior. I don't have like hard numbers or facts on how much better in like field trials or commercial deployments that TDD really is. I'm not sure if you, Emil, have any indication on that, but from academic studies, I mean, on measurements, it seems like, you know, you probably could expect TDD to be like 3 times as good as FTD. And I think that in the coming decade, we will see this consensus and awareness continue to grow. FTD is not going to go away because there are huge vested interests in infrastructure, perhaps in IPR, perhaps in other things, who knows. But I think with time, then we will see that TDD reciprocity is the way to go.
Yeah, so I mean, I think the starting point is that operators have FTD frequency bands with uplink and downlink at different frequencies, and then you can't use the type of massive MIMO that we have been describing, and then researchers have been trying to find a solution. And then there is, of course, this tendency, if you write a paper about how to deal with it, that you describe it that here is a good solution. But then it's also unfair to compare these type of things. So I think even the researchers that have been investing a lot of effort into developing FTD-like methods are people that if you talk with them, they say, yeah, of course you would like to do TDD mode. That is the best thing. But if you are forced to do FTD, here are our kind of solutions of how to do this to at least deal with some of the issues that appear.
I think you're right. I mean, obviously, if suddenly the world realizes that TDD is the way to go, we'll scrap all the current frequency regulations and all that and just redo from a clean sheet, then all these FTD algorithms are just going to be useless overnight, right? And quite a few folks don't want that. So that might be a factor as well here, yeah.
Yeah, and I think that we have sort of been saying for years that the people or operators in countries where FTD was previously viewed as being the main thing was much easier to use. And then people who was forced to get TDD spectrum, they were sort of in a disadvantage. And then we have been saying that, well, they will soon discover that they were actually in an advantage because now they're sitting on this type of spectrum asset that will, with the massive MIMO, grow a lot in value. And I think that is something that you can nowadays also hear echoed from operators operators and vendors as well that you really want to have TDD spectrum in the future.
That's interesting. I mean, reality might be catching up faster than we think, right? I mean, that's what happened with massive MIMO in general. I mean, 10 years back, nobody really thought that massive MIMO would be a commercial reality, that it would be the cornerstone physical layer technology in 5G by 2020. And now sitting here today, 2020, nobody might believe that, in 10 years, FDD is going to be on the trash heap of technology history and everything in the world is going to be TDD reciprocity based. Who knows? The future will tell.
Yeah, I think when I first heard about massive MIMO 10 years ago, it felt like science fiction, and I had this gut feeling that there must be something wrong here in the analysis because it can't be this good, because otherwise everyone would understand that it's good, and it didn't seem like people did that. But now we're here.
Perhaps the same with the TDD FDD, who knows?
Yeah, exactly. So what about the last few years? Have you come across any new myths? Some misconceptions that are spreading around?
Yeah, that's a good question. So I think there might be one that continues to disturb me. And it is the claim that massive MIMO, I mean, because it relies on spatial multiplexing, right? I mean, the main portion of the gains come from the ability to perform spatial multiplexing. Then for massive MIMO to actually deliver any gains, there has to be multiple users in the cell who want to transmit or receive data at a given point in time. And then when you talk with a lot of folks like working on practical networks, they tell me that, yeah, but when we look at actual data from current network operations, then what we see is that most of the time in the cell, there is just a single terminal, or maybe no terminal at all, but if there is anyone, I mean, there is just a single one who wants to transmit. So why would we need massive MIMO spatial multiplexing then? And I think the truth here is that yes, massive MIMO really relies on the ability to exploit massive spatial multiplexing, right? I mean, that's a fact. What I think is the myth is that future networks or the traffic in future networks will look like the traffic in current networks. I mean, just because we see in current networks that there is a single terminal that wants to send data at some given point in time, then who knows, in 10 years, I mean, we might have entirely new applications, right? I mean, there might be all sorts of new gaming applications that have evolved, augmented reality, virtual reality. There might be certain types of new machine learning that requires enormous amounts of training data to be fed through wireless links up to some learning center or processing center. And we'll see a structure of the traffic that's just fundamentally different, where we will have all these 20 or 30 terminals in the cell all the time eager to send data over the entire band. So that's what I think. And I think also a historical perspective is important here, because when the iPhone came, when was that? I think like 2007 or something, right? Then what the operators and vendors saw was that the pattern of the data traffic in the networks almost overnight changed entirely. Because of all these new apps and all new signaling and all that came with the iPhone, then suddenly, I mean, the nature of the packets that were sent over the wireless network just changed fundamentally. And who knows, I mean, I'm sure this will happen again, and we might not even be able to predict what will be the application that will cause this change, right? But what I'm fairly sure is that it will happen. And now, given that we have massive MIMO and we have this ability to multiplex 20 or 30 terminals, then there will be applications that require it. And we will see networks where we have all the time devices that are eager to send data over the entire bandwidth and just crave for this spatial multiplexing capability that the base station offers.
Yeah, I think I heard that when Sprint was turning on some of the massive MIMO base stations and tried them out in the network, what they saw was immediately those 8 times gains that they were expecting by having 8 times more antennas than before. Yeah. And that was also kind of showing that when the users in the shopping mall where they have deployed it were all of a sudden experiencing better coverage, higher data rates. They also started to use their phones more. I mean, if I'm in a situation where I can't stream something to my mobile phone because I have bad coverage, of course I'm going to stop. But if I could, I would probably do it. And I think we also have this sort of problem that we have been used to dimensioning network deployments in a particular way. You have been counting, okay, every base station have a fixed spectral efficiency or some average number. And now we need to count, okay, in this area, the users are going to expect this. And then we just putting up enough base stations to satisfy that. But when we are instead using a technology where we are able to say that this cell can support one user with this spectral efficiency. If we add one more user, well, then the spectral efficiency increases. So you don't need to share. Well, then that's a different game. And I think instead of putting up more base stations, we can then over time refine the hardware instead and keep the same type of dense deployments that we are having today.
And the need for all these bits and all this multiplexing will come. I mean, I think it's a bit like, suppose everyone was sitting at home with their PCs having a 64 kilobit modem connection to the internet, right? And then suddenly you would offered 100 megabit per second fiber, but you had no applications or software or video streaming applications or anything that could utilize that. And why would you want 100 megabit fiber? But as soon as the fiber is there, it'll take you within a year. I mean, we would have all this software that would use the bits. So I think it'll be the same thing with the wireless networks. I mean, once the technology, once the connectivity and these multiplexing gains are there, then the applications will come, and the corresponding structure of the traffic in the network will change accordingly. So we'll see it happen, I think.
Yeah, and I think last episode I was saying that in China there is around 500,000 of new 5G base stations, and I wasn't sure about whether they were using massive MIMO or not, but I have since then talked with an expert on one of the big vendors who are saying, well, indeed, it is 32R or 64T64R base station that they have deployed almost exclusively, which is sort of showing that now the operators have realized that this is what they really are needing in the networks, and they might not need them all the time, but you are dimensioning networks based on the peak hour traffic the users need in those times, and then maybe in the nighttime you won't need any of these functionalities, but that's not what you're dimensioning networks for.
Yeah.
Okay, so I think we are reaching the end of this episode of Wireless Future. And if you have any questions or thought about the things we have been talking about, please feel free to contact us. We might be talking about questions in future episodes, for example, and you could send us email, you can comment on the YouTube video, or you can, of course, subscribe both to the podcast version and our YouTube videos if you would like to listen into further episodes in our Wireless Future.
Yeah, thanks a lot, and bye-bye.
Thank you. Bye-bye.